Anyway, so let me start with a very simple question that even if you have mainly Newton's law, which is very efficient law and very natural in a sense to understand the system, why you need a different way or different approach to learn the system? And that is mainly known as what? Classical mechanics. Why we need some new method to understand the system? So if you have any answer or if you have any intuition about that, can you please tell me? Anyone? Sautan, can you please tell me why we need classical mechanics? In spite of that, we have Newton's law of force F is equal to ma. We can solve this thing, but why we need classical mechanics? What are purpose to understand classical to learn new topic such as classical mechanics, Lagrangian formulation or Hamiltonian formulation? Yes.
Sir, actually Newton's law completely they problem to solve problem. Like if we have particle, it's
Okay,
okay
आपका
solve
इंटरनेट थोड़ा अच्छा नहीं है.
through
Sorry,
Newton, but
sorry, Sautan, your internet is not good, so I am not able to listen you. Jitendra, can you please tell me?
Sir, what happens in
Sir,
Newton's mechanics
Yes.
is
sir, it is audible.
Now it is audible. Yes. Yes.
Sir, actually, we are actually Newton's law is a vector, and the huge problem if the system is any particle or body. So
Okay,
we
okay.
are going to a new method with some killer formulation.
Okay, okay, good. So,
That's why.
okay, good. Thank you. So, first answer is that he tell all about the mathematical easiness. Isn't it? Mathematical easiness. Why? Or you can say mathematically it is more easy. है ना? Mathematically more easy to work in scalar quantity rather than vector. Good. Okay, yes, Newton's law is absolutely vector calculation. We have to talk about the direction. We have to talk about the thing. So yes, Newton's law is all about vector calculation. But yes, Lagrangian, Hamiltonian, and in the classical mechanics, we are more generally talking about the scalar one. Okay, good. I appreciate your answer. So let's go for a second thing that other than this, anyone have an answer? Jitendra, can you please tell me?
sir, in Newton mechanics, force
Mhm.
plays a major role. Like first we have to calculate the force acting on the body.
Yes,
Then we calculate acceleration by dividing the mass,
very good.
and then the rest of the physical quantity. But what
Okay,
happens in Lagrangian? Here we are using energy, which we
that is
have
the
written.
same thing. That is same thing, Sautan tell that in the Newton's law we are using the vector calculation. So here we are calculating the force and then after doing the thing.
Yes, sir,
And
yes.
and yes, obviously from this particular Lagrangian or Hamiltonian, we are working with the energy that is a scalar quantity. That is same thing. You are more or less talking about this. Other than this thing, anybody have any other clue?
Yes, sir, we don't have to account for the constraints in Lagrangian formulation.
Sorry. Uh-huh.
We don't have to account for the constraints in Lagrangian formulation.
No,
That makes
constraints. No, constraints is just one type of tool which will help you to solve the Lagrangian. It will just allow you to get the independent coordinates. Okay, constraint is always there. Either you are working with the Newton's law or you are working with the mainly Lagrangian formulation. Constraints are always there. So constraint is not the thing. Constraint is all about finding the independent number of variables, isn't it?
So to make our calculation simple, which we are not able to solve in Newton's
Okay, that is the same thing.
Newtonian
That is the
mechanics.
same thing. That is the same thing. Okay, other than this one, simplicity ke alawa. Obviously, one guy have told about the constraint, but I don't think constraint is the differentiation part of Newton's law or here. Both places we use the constraint thing. Okay, and because due to constraint, once we will calculate all the constraint, then only we can easily get the independent coordinates, and then we can solve this thing. Other than this thing, okay, now look at here. The first thing is obviously simplicity. It's 100% correct that yes, simplicity is the thing where we are going for the basically Lagrangian formulation, mainly for if we are talking about more number of particle. If we have n number of particles, not 2, 3, 4 number of particle in our system, then obviously doing the calculation of Newton's law is very tough. But if we are going for the Lagrangian formulation or the Hamiltonian formulation, we can usually analyze the number of, if we have more number of particle. That is also part of simplicity. But the most important thing is that, listen, if we are doing the Lagrangian formulation or Hamiltonian formulation, and before that we are doing the Newton's law. In the Newton's law, we can talk only about the conservation of momentum, mainly conservation of angular momentum if you are rotating system, and at far up to some level you can go up to conservation of energy. But in the nature, there are n number of things which can be symmetric. There are another different type of physical quantities which are symmetric, which can be also conserved. So Newton's law of motion is not enough smart to tell you all about the different type of conservation law. Different, you can stick only up to level of momentum or angular momentum or energy. But if I am talking about any particular constant or some hypothetical thing, some mathematical thing, and I just want to see whether it is conserved or not. So it is very difficult in a Newton's law that new type of conservation, new type of symmetry cannot be revealed by the Newton's law. But here you will see, we will discuss a different type of symmetry from the Lagrangian formulation as well as mainly from the Hamiltonian formulation. So second thing is that Lagrangian, or in the classical mechanics, we can explore new symmetry of system. So this is a very interesting thing from my point of view for classical mechanics. You will see the previous year paper. If you have some opportunity, you will see that somebody will give you one particular expression and they will ask you whether this quantity is conserved or not. And you don't know what is the name of that particular quantity. And even if you don't know the name of that particular quantity, you can easily analyze mathematically whether it is conserved or not. So this is one of the very interesting point of view to learning the mainly your Lagrangian and Hamiltonian formulation and mainly classical mechanics. And third one is it is the most important thing. We have to go from macroscopic system, to microscopic system What will happen from the macroscopic to microscopic system, the all nature of a system is going to change. And here we are using the Newtonian mechanics easily. Newtonian mechanics. And here we will use the quantum mechanics. But the journey of Newtonian mechanics to the quantum mechanics is not discrete. It is not just a black and white kind of thing that you have white here and black here, or black here or white here. There are the gray areas, and these gray areas can be covered by all our classical mechanics, and we will learn the formulation of quantum mechanics from itself, from the classical mechanics. Okay, so it is very important to learn classical mechanics. The Hamiltonian formulation itself, Hamiltonian formulation is the part of quantum mechanics. But obviously here we are using it just operator, but that is the same Hamiltonian we have in the classical mechanics. So the journey from macroscopic world to microscopic world is delivered by mainly from the classical mechanics. And the next part is that in the Newton's law, mainly we can work for the linear system. Up to the linear system, your force is linear. Up to that, you can solve that everything in a very nice way. But when you want to go for the non-linear system, again, classical mechanics will help you to go from the linear to analyze the linear system to the non-linear system with the help of phase space or different kind of concept. So it's a very wide topic. It's a very important topic to understand the system. Okay, so you cannot ignore this particular topic, because each and every point will leads to some new topic. And you will see that once we will learn the phase space into classical mechanics, that same thing can be explored into the statistical mechanics. We will learn the commutation rule or Poisson bracket here, the same kind of situation we have into the quantum mechanics. So it's a very fundamental topic which will allow you to learn the modern physics in a very efficient manner. So why we have this particular concept of Newton's concept of classical mechanics. So the first part of classical mechanics is all about Lagrangian formulation. So, but most important thing is after Lagrangian formulation is nothing but more or less equivalent to Newton's law, we will see. But it is the different method to write the Newton's law. We will try to understand each and everything. But before that, let us go for some basic definition of classical mechanics. Up to that, if you want to add something, you can easily add. This is just a warm-up class for us. Okay, we will just try to see in which direction we have to go. So this is just a warm-up class, the fundamental class, you can say. From the next class, we will just go into the deep of this particular topic. But before that, if you want to add something, please, you can add. Okay. So, what are the classical state of a system? Classical state of system. And why we learn about the state of a anything? You will learn quantum mechanical state, you will learn thermodynamical state, you will learn classical state of a system. So what is classical state of a system? Mahima, can you please tell me what is classical state of a system? You can just talk to me, है ना? Otherwise, it's a very boring class. Okay?
Yes, sir.
चलो बताओ महिमा, what is classical state of a system? जो भी आता है बताओ. In the classroom, we have to learn, है ना?
Sir, I don't know.
You don't know?
Yes,
फिर भी
sir.
क्या लगता है क्या होना चाहिए? फिर भी just try. Senapati, can you please tell me what is classical state of a system? Anybody else?
Defining its position or momentum.
Defining its position and momentum. Exactly. If you can define the position, let's say I am just talking about right now one dimension. So position and its momentum px, then we are saying we know the classical state of a system. So in general, we are talking about position and velocity, but yes, momentum is more efficient thing because we need to know that what if some heavy mass is moving with the same velocity with the smaller mass or lighter mass, then effect is different. So why we take the momentum in the case. Otherwise, the position and its momentum or position and its velocity, its conjugate velocity. What is meaning of conjugate velocity? Means x direction position, then the velocity in the direction of x is the conjugate one. You cannot say that x and y dot are your state. No, you cannot say. You can say x and x dot can be your classical state. And yes, if I can add the mass, then we have x and px is my state of a system. Sorry. So if you know the state of a system, what are benefit of that? What are benefit of that? Ananya, can you please tell me? If you know the state of a system, what are benefit? Why you need to define the state of a system?
Sir, then we can
Mhm.
analyze its motion and other properties.
Obviously, you can analyze the different type of physical quantity. Once you define the state of a system at some time t, you can analyze all other physical quantities. All other physical quantity. You can say your physical quantity can be energy. You can say your physical quantity can be angular momentum. And even you can discover some new physical quantities also. But in the classical mechanics, once you know the state of a system, and then you can easily analyze all possible physical quantity, how they are evolving with the time. The most important challenge is that we have to see what are our basic physical quantities and how it is evolving with the time. It is most important thing. And the evolution of any physical quantity with the time is basically defined only and only if we know how my state is evolving with the time, how my classical state is evolving with the time. So evolution of physical quantity, time evolution. Time evolution of physical quantity can be analyzed if we know the time evolution, of state, of classical state. Okay. So if you know the time evolution of classical state, you can easily justify all other physical quantity. By the way, what is time evolution of classical state? How do you know about the time evolution of classical state? From where you know the time evolution of classical state?
We simply observe, we see the change.
Yes. So is that any mathematical form of that time evolution of of this particular state?
I'm not getting so.
Newton's law of motion, equation of motion, isn't it?
Oh, I didn't get the question. Sorry. Sorry.
So if I am talking about time evolution of a state, that means I am talking about how my position and momentum is evolving with the time, and who will tell us that how this position and momentum is evolved with the time? Then obviously the equation of motion. So once you know the equation of motion, so our main target of mechanics or classical mechanics or Newton's law or Lagrangian is to identify equation of motion. Okay, we have to identify what is y equation of motion, and this equation of motion is nothing but more or less second order differential equation, and this can be function of x dot t and all about this thing. So this is more or less my equation of motion. So our main challenge is that how I will get this equation of motion. One way we know from the Newton's law, but it is very difficult. We will try to learn, get this equation of motion from different way, and that different way can have different type of formulation, and that is known as Lagrangian formulation, Hamiltonian formulation, and all other different Poisson bracket formulation is the another one efficient method. So we will see the final outcome is just this second order differential equation. This is the beauty of this particular Lagrangian or Hamiltonian formulation. Okay, so these are some basic intuition you have to know before starting your subject. Okay, now let me ask you the last question about the intuition based thing or definition based thing, that what is the property of basically classical system? What are the property of measurement of classical system? What are the property?
There is no
The measurement of
there is no in the measure.
सॉरी आपका इंटरनेट थोड़ा काम साथ नहीं दे रहा आपका. आलोक मिश्रा जी, कैन यू प्लीज टेल मी? What are the property of classical system? Very good. So answer is, he's just saying no error into measurement of, obviously, the measurement of classical system. The measurement of classical system is deterministic in nature. Deterministic in nature. What is meaning of deterministic in nature? If I know the state of a system at t is equal to t, I can easily predict with a 100% guarantee where will be system and what will be the physical quantity after time t is equal to t plus delta t. So this is very important thing. The measurement of classical system is deterministic in nature. That is not probabilistic, but in quantum mechanics you will see that the measurement is itself probabilistic in nature. It may be possible, it may not be possible in the quantum mechanics, but in the classical mechanics you will see, yes, I can give the guarantee that if I know what is my system at t is equal to 0, I can give you guarantee where will be my system after time t is equal to t. So there is not any error involved into the calculation. If you are doing the same experiment again and again, you will get exactly same path, exactly deterministic path for your particular system. So this is very important thing about my classic, but in the quantum mechanical system, there are error. And so why there are a lot of uncertainty principle. But in the classical mechanics, there are not any type of uncertainty principle. We are 100% sure that, okay, this is my situation, and what will happen after this? The system is deterministic, predictable, with the full of confidence. This is all about classical system. Okay.
Sir, but surrounding situation should be same.
Obviously, I am just
No,
if
no.
I am talking about system, that means its potential will be same, its mass will be same. If both thing will be, any of these two thing will be changed, then system is going to new system.
Okay, sir.
है ना? So obviously, if you are talking about surrounding, I am just saying what is meaning of surrounding. That means potential or force acting on this particular thing. So if I am talking about one system, that means it is assumption that yes, surrounding is not going to change. If I have actually the same surrounding, same potential, same force, then you can repeat the experiment again and again. You will get the exactly same deterministic form of answer. Okay.
Yes, sir. Okay, sir. Thank you, sir.
Okay. So now one most important thing is that to learn before a Lagrangian formulation is degree of freedom and equation of constraint. So first we will go for equation of constraint. What is meaning of constraint? Meaning of constraint is all about restriction. But before that, let me ask you, what is meaning of dynamical variable? So there are two type of thing. One will be variable, another will be parameter, and another will be constant, some universal constant. So what is variable? If I am talking about variable, I am just talking about vary with time. So why we are just saying dynamical variable. So what is dynamical variable? Suppose I am saying that, okay, my Q is some dynamical variable. What is meaning of that? Anyone? आपको पता है, but आप बता नहीं पाते हो.
The value of Q will change, or it depends on our assumptions and situation or scenarios.
You just okay. Just
It
एक line
will
में
change with time. It will change with time.
that will change with the time. Okay. So basically, if I am saying, suppose I am talking about dq upon dt, which is not equal to 0, then I can say Q is my dynamical variable, isn't it? That means just Q is just a dynamical variable. The total derivative is not changing with the time. I'm just talking about total derivative. Okay. Now, what are parameters? Yes. Those variable which is not changing with the time, isn't it? है ना? So parameter, you can have some variable dq upon dt is equal to 0. Then this is known as parameter, or some constant value, constant parameter. Okay. That value for the system, that value will remain always same. For example, simple pendulum. If I am talking about simple pendulum, then the length of this pendulum will always remain same. Okay. So this is one type of constant we are using, one type of parameter, long pendulum, short pendulum, isn't it? So we can change the parameter. But one particular system, we have fixed value of this parameter. And what are universal constant? Obviously, in the classical mechanics, my universal constant is what? G, gravitational constant, in general. Okay. Other topic have another universal constant. For example, thermodynamics, you have another universal constant, that is Boltzmann
Boltzmann.
constant. Yes. In the quantum mechanics, we have very beautiful universal constant, that is h cut.
Planck's.
Yes. Great. Isn't it? So these are our, in the electromagnetic theory, we have some epsilon naught.
Probability.
है ना?
Yeah.
Yes, we can have this particular epsilon naught. So these all things are there. So we have this particular dynamical variable. Okay. Now, one very important thing is that a lot of people are confusing with the explicit function or not explicit function. So let me explain you. If I am saying any function f is explicit function of time, explicit function of time, what is meaning of that?
It depends explicitly on time and no other variable.
Okay, that is in the English. I just want to know mathematical language. How do you check whether it is explicit function of time or not?
We differentiate it with some other
Oh, very
quantity.
good,
It
very
won't
good,
change.
very good.
It would
So
be
it's a total derivative or partial derivative?
Partial.
Exactly, it is partial derivative. Okay. So if you have del f upon del t, which is not equal to 0, then f is explicit function of time. But if del f upon del t is equal to 0, that means f is not explicit function of time. In general, df upon dt is equal to not del f upon dt. Okay. Can you please, okay, we will discuss it. In general, total derivative is not equal to partial derivative. You have to always take care of this particular thing. Only one physical quantity is there. Only one physical quantity is there whose total derivative is equal to partial derivative. Do you know that? Do you know that particular physical quantity? We will discuss. We will discuss. Don't worry. I am just giving you clue. There is only one physical quantities whose total derivative is equal to what? Partial derivative. Other than it is not necessary that total derivative is equal to partial derivative with the time. It may be equal. It may not be equal. In general, they are not equal. Okay. So we will discuss this thing when we will go for time evolution of physical quantity with the Poisson bracket. Okay. But before that, we have to do a lot of work on this particular thing. So up to that, if you want to add something, you can add it.
Yes, sir. About that deterministic nature in classical mechanics.
Mm-hmm.
So Richard Feynman said, the very brief. He gave an example of a random drop falling a little off from the track in a dam, and we don't really know the path it's going to follow, and we call it deterministic, and it's kind of a misnomer.
Maybe I am not aware of this. Okay, give me that thing.
Yes, sir.
But I am just talking about a macroscopic particle in general, where we can write the force equation. Okay,
Yes,
if we can write the force equation, then obviously it's deterministic in nature. Okay.
Okay, sir.
Okay. Maybe you can send me what is the article. Maybe I am not aware of that. Okay, it will be also
Yes,
privilege for me. ठीक है? Okay.
Sir,
हाँ, बोलो.
sir, in classical state of a system, there is
Mhm.
x comma px.
Mhm.
Sir, why we not take the initial time, that is
Time is
T0
the
or
inherent part of
some-
any dynamical system. Don't worry. Time is always there. Okay. Time is always there. So it's a very, you can see that every philosopher, every mathematician, and even everybody is little bit of confused with the time, that whether time is physical quantities or not physical quantity, okay, and or it is just like some perception. It is very difficult to say. Okay, so why in the quantum mechanics you will see there is not any operator for the time. Time is the just a inherent part of any dynamical system. Okay,
Okay, sir.
and it is moving just only in one direction. Okay, it is just moving in one direction, unidirectional. Time cannot be reversed. There is time reversal concept in some other way, but in the classical mechanics, we are just pointing time. The time have only arrow which can move, and it's a very difficult thing to analyze the time as a physical quantity or not. Okay, it has. If you want to learn something about time and entropy and all this thing, you can learn in the Brief History of Time by Stephen Hawking. Okay, he just give all these things, what is time, how we can perceive time. So why we have taken time as a reference thing, isn't it? Velocity dx upon dt, reference by with respect to time, isn't it? Force, rate of
That
change
means
of
it always.
yes.
Okay, sir. Okay, sir.
And time is something for the reference. So why it is always in the denominator, isn't it? Velocity, acceleration, everything have dv by dt, rate of change of velocity. Okay, so time is always there, so you cannot ignore time. Okay, it may be explicitly mentioned or it may not be explicitly mentioned, but time is always there, isn't it?
Okay, sir.
So why I have told about the explicit function of time or not explicit function of time. Your physical quantities can be explicit function of time or it cannot be explicit function of time. It will depend on situation, it will depend on our system. Okay.
Okay, sir.
Okay. Okay, so let's go for equation of constraint. Why we need equation of constraint actually? Because it is very easy to solve the problem or analyze the problem if we have independent variables. What is beautiful part of independent variable? Let me give you one example. Okay, suppose I have choice of three number x1, x2 and x3. Suppose there is I have choice of these three number, and if there is not any relationship between these three number, I can freely choose x1, I can freely choose x2, I can freely choose x3. Yes, but suppose I have x1 plus x2 plus x3, then how many quantity I can choose freely out of these three? Is that all three?
Two.
Or two or one? Obviously two. Why? Because you can choose any two freely, but third, sorry, x1 plus x2 plus x3 is equal to 0. Let us have this type of relationship between all these three. Then what we have? We can choose x1 freely, x2 freely, but x3 must be minus x1 plus x2, isn't it? You can have another option. You can choose x1 freely, you can choose x3 freely, then x2 must be equal to minus x1 plus x3. And similarly, you can choose x2 and x3 freely, then x1 must be dependent on this. Similarly, if I give you one more equation, something like this, x1 is equal to x2, then how many variables you can choose freely? Then how many variables you can choose freely? Obviously, only one variable, isn't it? Because x1 is equal to x2, and then when you will put x1 is equal to x2, then what will happen? When you have, let's say x1 x1 plus x3, and here we can choose either x1 freely, that will be equal to 0, or x3 freely. We have to satisfy this equation 2x1 plus x3 is equal to 0. That means we can choose only one variable freely. And this is very interesting thing. So to analyze the system, we are making a provision that if we can understand this, if we can choose a independent variables, and if the variables are independent, then we can analyze this variable independently, we can analyze this variable independently, we can analyze this variable independently, and the whole system will be obviously mixture of all variables. But it is the very nice way to analyze the system independently first and then combinedly with the same, with the all this thing. So to finding the independent variable, we need equation of constraint. We need equation of constraint, and equation of constraint is nothing but relationship between variables. So let's go for a two type of equation of constraint. Suppose we have dynamical variable. We have dynamical variable q1, q2 up to q3. Let's say qn, n number of dynamical variable. We can have n number of dynamical variable. And what we have two type of constraint. First is holonomic constraint. What is holonomic constraint? If relationship between variables, so these are variables, let's say qn, can be represented in a form of equation. If relationship between dynamical variable, I am just talking about dynamical variable, if relationship between dynamical variable can be represented in a form of equation, then this type of constraint, this type of restriction equation is identified as holonomic constraint. For example, you can say a particle is moving in a circle in xy plane. So this is a story. How you can write this story in terms of mathematics? You will write, okay, the particle is moving. So suppose this is my origin and this is my x, y, or z. Suppose the particle will free, then I have x, y, and z as my variable. Suppose I want to solve it into just a Cartesian coordinate system. We will discuss all about the coordinate transformation also. But this particle of mass m is not free. It is moving in xy plane. So it is moving in xy plane means z is equal to 0. And it is not moving freely in xy plane, it is moving in a circular track in xy plane. That means there is a relationship between x and y, and it will follow the locus of circle for a particle. So you can see the relationship between variable, the restriction about the motion can be represented in form of equation. So why this is identified as holonomic constraint. So this is my first constraint, this is my second constraint. Are you getting my point?
Yes, sir.
Everyone? So we will do a lot of problems on this. I am just giving you the basic definition. So this is identified as what? Holonomic constraint. So you have to write the thing in form of equation. This is all about holonomic constraint. And now, what is meaning of non-holonomic? Obviously, the relationship between variables q1, q2, qn can be written in form of inequalities. In form of inequalities, then it is identified as what? Non-holonomic constraint. So this is, for example, suppose I have gaseous molecule and gaseous molecules are in milli box. Let's say this is my gaseous molecule in the box and the length of box is, let's say, Lx in x direction, Ly in y direction, Lz in z direction. Then obviously any gaseous molecule, let us assume there is only one gaseous molecule, is this one. So this will be between, x is between 0 to Lx, isn't it? Similarly, y is between 0 to Ly. Similarly, z is between 0 to Lz. So this is not in form of equation. These are in form of inequalities. So these type of constraints are known as non-holonomic constraints. Okay. Up to that, are you people comfortable? We will do a lot of problems. Don't worry. We will do a lot of problems, but I am just giving you the basic definition right now. Everyone is comfortable?
Yes, sir.
Okay. Okay. So I think this is our first class. So I will stop all this thing here. Tomorrow we will go for again holonomic constraint and degree of freedom, because both are related to each other. We will also discuss why non-holonomic is not part of degree of freedom, and then we will go for different type of coordinate transformation. Why we need different type of coordinate transformation, we will also discuss this thing. Okay, and then we will go for Hamilton's principle. This is basically, or generalized coordinate, generalized velocity after degree of freedom, and then we will go for Hamilton's principle. Okay, so I think tomorrow we will just go up to degree of freedom. After next class, we will move in the next level. Okay, so are you people comfortable?
Yes, sir. Very
Yes, sir.
Mhm. Any suggestion with my language or writing or something else? The space is okay or little bit faster or slower?
No,
सर
sir, everything is
Mhm.
perfect.
Okay, thank you. Yes.
सर
बोलो.
सर मुझे थोड़ी प्रॉब्लम हो रही, मतलब ऐसे इंग्लिश में
इंग्लिश में आपको दिक्कत हो रही है?
जी सर।
अच्छा, तो कहाँ प्रॉब्लम हो रहा है वो बताओ. जैसे
सर मतलब थोड़ा समझाने में थोड़ा हिंदी आप थोड़ा सा यूज करेंगे तो मुझे
ठीक है,
अच्छे से
ओके.
समझ में आएगा,
ठीक
क्लियर
है,
हो
ठीक है,
जाएगा
कोई
बिल्कुल।
दिक्कत नहीं.
और
आप देखो,
वैसे
आप कहीं भी आपको नहीं समझ में आए, आप तुरंत हिंदी में पूछ लो, मैं उसको
जी
तुरंत
जी
हिंदी
सर।
में बात कर लूंगा. ठीक है,
ओके
वेरी
ओके
गुड.
सर, थैंक यू
लैंग्वेज
सर।
हिंदी में तो मेरी मदर टंग है, तो हिंदी तो मेरे लिए बहुत आसान है ना.
जी हाँ सर, वैसे वैसे
So,
मुझे कोई डाउट होगा फिर मैं वो आपसे पूछ लूंगी।
एकदम आप क्लास में बेझिझक किसी
ओके
भी
सर।
समय में आप पूछ सकते हो. यू कैन,
ओके सर।
आप मुझसे पूछ सकते हो, हिंदी में पूछ सकते हो, इंग्लिश में पूछ सकते हो, थोड़ा बहुत उड़िया, थोड़ा बहुत बांग्ला, थोड़ा बहुत पंजाबी में पूछ सकते हो. मैं हिंदी या इंग्लिश में बताऊंगा. ठीक
हिंदी
है.
ठीक है, उड़िया बंगला तो नहीं आता।
थोड़ा बहुत मैं ये सब भी समझ लेता हूँ, है ना.
हाँ सर सही है।
ठीक है, तो
ठीक है
डोंट
सर।
वरी. देखो, सबसे इंपॉर्टेंट बात यह है कि हमें क्लास को इंटरेक्टिव बनाना है ना, नॉट मेक इट बोरिंग ऑल अदर ऑनलाइन क्लासेस टाइप थिंग. ओके,
यस सर जी।
है ना. सो
Yes.
ये मेरे लिए भी अच्छा रहेगा, क्योंकि एक ही चीज मजा नहीं आता है फिर, है ना. एक तो दिन भर कैमरे को देखते रहो, एटलीस्ट
हाँ सर।
एटलीस्ट आपकी आवाज सुन करके तो लगेगा कि मैं ह्यूमन को पढ़ा रहा हूँ. Isn't it?
जी सर बिल्कुल।
So don't feel shy to ask question. But yes, we will mute ourselves जब मैं कह रहा हूं तो, और फिर उस हिसाब से जब भी आप बात करोगे तो हम लोग बहुत आराम से एक दूसरे को सपोर्ट कर सकते हैं, है ना, जिससे कि क्लास भी डिस्टर्ब नहीं हो और चीजें काफी अच्छे से चलती रहे. एंड डोंट वरी अबाउट डाउट्स. कन्वर्सेशन हम लोग एक दूसरे से बात करके ही चीजें करेंगे. ठीक है,
ओके सर। ओके
ओके, डोंट वरी.
थैंक यू सर।
हाँ, और फिर कोई सजेशन, एनीबॉडी एल्स?
सर
बोलिए.
can you say something about in first and conservation law. Can you say something about symmetry?
Yes. Okay. Good. You want to talk about symmetry. It is my favorite thing. What is meaning of symmetry? Symmetry is just like a conservation law, isn't it? Okay. Momentum is symmetric. What is meaning of that? Momentum is conserved. What is meaning of that? Angular momentum is conserved. What is meaning of that?
That is initial momentum and
Final momentum will remain
are
same.
same.
Okay. So you can say this linear momentum is symmetric in space. What is meaning of that? If you will do one experiment in this particular room, okay, and then you will translate the whole experiment in some another room. Are you getting my point? Then what will happen?
Sir.
You will have conservation of momentum there also. So it is symmetric in space. Similarly, you can rotate the whole thing and then you can measure the thing. You will have symmetric this kind of thing also. That is angular momentum. Angular momentum is symmetric about angle, isn't it? If angle is changing. Are you getting this thing? So
Yes, sir, yes, sir.
symmetric means that thing will remain same after doing some transformation. So that is different. That is one type of conservation law. If I am talking that, okay, my energy is conserved, that means my energy is symmetric with some variable. What are that variable? Just I am giving you one very nice intuition. Have you heard about the uncertainty principle?
Yes, sir.
Yes, you have heard about uncertainty principle. What is uncertainty principle? Delta px into delta x. एक तो ये पढ़ा होगा, और क्या पढ़ा?
Energy time.
Energy and time.
डेल्टा ई और डेल्टा टी भी पढ़ा, और भी कुछ पढ़ा क्या?
Any conjugate pair, sir.
Any conjugate pair, very good. डेल्टा LZ और डेल्टा थीटा भी पढ़ा आपने.
Yes, sir.
Isn't it? So you have learned all this thing. So whenever we are talking about the conservation of momentum, then space will come into picture. And when we are talking about conservation of energy, then this time will come into picture. And when we are talking about conservation of angular momentum, then this theta will come into picture.
So is it mean that homogeneous space?
Yes, the momentum is homogeneous in a space variable, linear space variable.
Okay.
Angular momentum is homogeneous in angular space variable. Energy is homogeneous in time variable. और ये सबका अलग अलग प्रूफ है, ठीक है? And by the way, what is conjugate variable?
Okay.
Chalo. Anyway, so I think you got the meaning of symmetry, na? Hello.
Yes, sir.
हाँ, अभी इसके बारे में डिस्कस करेंगे. Don't worry, we will discuss a lot of things.
Yes, sir.
हाँ, हेलो, आपकी आवाज नहीं सही आ रही है ना? ठीक है, चलो फिर आज के लिए इतना ही रहने देते हैं, है ना? सो टुडे इज फर्स्ट डे, सो कल हम लोग थोड़ा सा इसको और आगे बढ़ाएंगे, ठीक है? थैंक यू.
Okay, sir. Thank you, sir.
थैंक यू.
Thank you, sir.
Yes, sir.
थैंक यू.